All right, Lagrange's theorem is a very important theorem. Um, so basically, we have seen with the cyclic groups in the fundamental theorem of cyclic groups, we saw that the order of a subgroup divides the order of the so if I have a subgroup of a cyclic group, then the order of the cyclic group, the order of the subgroup divides the order of the cyclic group. Now this is just generalizing that to any finite subgroup, sorry, any finite group. So let's say G is a finite group and H is a subgroup of G, then the order of H divides the order of G, right? So again, when I say order of H, it means the number of elements in H, and order of G means the number of elements in G. So let's try to prove this, and the proof of this is kind of long, so I'm going to break it up here. So to prove this theorem, we first need to establish a lemma, an auxiliary result here. So let's let H be a subgroup of the finite group G. For A, B, and G, define, actually in this lemma I don't even need that G is finite, but we're going to apply that when G is finite. So let's let H be a subgroup of the group G. For A and B and G, define the relation tilde as follows. A is related to B if and only if the AB inverse is in H. So the relation tilde depends on H. Then a tilde is an equivalence relation on G. So, well, we want to show that this relation is reflexive, symmetric, and transitive. So for any A in G, we have that A times A inverse is the identity, which by definition of a subgroup, it belongs to any subgroup. So E belongs to H, so I see that A inverse is in H, and by the definition of tilde, then A is related to A, and this is for any A, so it shows that this relation is reflexive. For any A, B, and G, if A is related to B, that means that AB inverse is in H. And since H is closed under inverse, then if AB inverse is in H, then the inverse of AB inverse will also be in H. So if I take the inverse of AB inverse, that's going to be in H, but that is equal to BA inverse, and because BA inverse belongs to H, then obviously B is related to A. So then I see that tilde is symmetric as well. I'm going to leave it as an exercise for you to show that this relation is transitive as well. Okay, so the next step is the following. So let's say that G is a finite group, H is a subgroup. Let's say the order of G is n and the order of H is m. And let's let tilde be the equivalence relation that we defined in the previous lemma. And we know that tilde is equivalence relation, so then we can talk about the equivalence classes. And recall that the collection of distinct equivalence classes is denoted by G/tilde. This is the distinct classes of tilde form a partition of G. And the number of classes would be finite because G is finite. So we defined a relation on the group G, and we got an equivalence relation, and so the distinct classes will form a partition of G. So when I say that, it means that the number of elements in the total number of elements in the distinct classes is the same as the number of elements in G, right? So every element of G is in one of the distinct classes. So we will show that the order of each of the classes is equal to the order of H. So now what I'm going to do is show that the number of elements in each of the classes is equal to the number of elements in the subgroup H. How do I do it? Well, I'm going to establish a one-to-one function. So we're going to define a one-to-one correspondence between a class and the subgroup H. So given A and G, define the function rho A from H into the class containing A. So for any A and G, consider the class containing A and define a function rho A from H to the class by the following. Rho A evaluated at H is equal to H times A for any H in H. And you can show that this function rho is a one-to-one correspondence, that it is injective and surjective, so it's a bijective mapping. So if it is a bijective mapping, then because the domain and the codomain here, they are finite, so then I can say that the number of elements of H is the same as the number of elements in the class containing A. So that means every class under this relation has the same number of elements. That is, each class has as many elements as the subgroup H. And I'm going to leave it to you to prove that the function rho A that we defined is both injective and surjective. So then it follows that the number of elements in H is equal to the number of elements in the class containing A. So each equivalence class then has M elements. Remember, M is the number of elements of H. So each equivalence class has M elements. Now, since the classes the set of distinct classes form a partition of G, which means that every element of G is in one of the classes. That is, the total number of elements in the classes is the same as the number of elements in G. So I can say the number of elements in G is the same as number of elements in one of the classes multiplied by the number of distinct classes. And so from this we see that the order of G is equal to M times the number of distinct classes. M here is the number of elements in the class here, which is the same as the number of elements in H. So we see that the order of H, which is M, divides the order of G, and that completes the proof. Okay, so now two consequences here. If G is a finite group and of order n, and so the number of elements of G is n, then for any A in G, the order of A divides n, right? The order of an element of a finite group divides the order of the group, right? This is what we're saying, that the order of an element of a finite group divides the order of the group. Why? Because the order of A is the same as the order of the subgroup generated by A, which divides the order of the group by the previous by Lagrange's theorem. And number 2 says for any A in G, A to the power n is equal to the identity. That is, A to the power, what is n? N is the order of the group G, right? So for any A to the power, the order of the group is equal to the identity. So if you raise an element to the order of the group, you always get the identity. Why is that the case? Well, by 1, n is a multiple of the order of A. So if n is the multiple of the order of A, then obviously A to the n is the identity. We have seen that before. Okay, so I guess the next few slides we have a bunch of exercises, and so I will stop here. All right, so if you have any questions, please bring them to the class, and I will answer your questions as much as I can. All right, so see you soon. Okay.